Well, thanks everyone for attending. This is a huge crowd, so I really appreciate you guys showing up. My name is Chris Dutra. I run site reliability engineering at Schireson. Schireson is a data science company headquartered in New York City, and we do qualitative, quantitative market research, as well as data science and media optimization. Long story short, we help our clients with a variety of different things in marketing and advertising. You can find me on GitHub, you can find me on Twitter, links here. And also, after this presentation, you have any questions or anything like that, you know where to find me. I'll be wandering around. I want to talk briefly about Schireson and kind of the journey we've had. They've been around for about 10 years. I've been with Schireson for about 9 months now. And for the last year or so, there's been a transition from a services organization to a product organization. What that really means is that we have data scientists that typically would put this work together and send it off to a client. And our job as engineers has been to build the data science processes and actually make them a platform that is a service for the clients to be able to run the data science workloads themselves. So part of the reason I'm here, because we are running Kubernetes. We're using a lot of neat technology, and due to the advertising industry and kind of not really having any regulations, we can pick and choose the different types of tech that we want to work with, which is really neat. So there were a lot of interesting requirements that we had when we were moving data science code that typically lived in a Jupyter notebook into a container. So that was an initial hurdle, thinking of data scientists writing things to their hard disk on their laptop, and then using that, putting that into volumes. We had to do a lot of that kind of retrofitting for those processes. Also, in order to get our clients to actually use this instead of calling the data scientist, we had to achieve at least similar performance to what a data scientist was running on a laptop. So they had big, beefy desktops that we'd be basically competing with a Kubernetes cluster. So that was another interesting challenge. And also, as I mentioned before, providing data science as a service to clients. So we had to make it intuitive, we had to make it easy. They had to understand what they were doing, as they were adjusting different parameters or choosing different data sources. So these are all things that kind of came into how we started moving these data science workloads into a production grade cluster. So our first attempt at this was, well, let's try to put this into a deployment. That did not work out too well. As you can see, there's a lot of spikiness with data science processes. We had a lot of evicted pods. We had a lot of killed nodes. It took us a long time to realize that the traditional way of deploying an application was not going to work for data science. Also, you can see from here, this is actually memory in our Grafana. It takes up a lot of memory. So we also realized that isolation was pretty important. We didn't want to run or have an issue of evicting different APIs or back-end processes, because the data science processes were going to take up all the memory and resources and potentially even bring down nodes. So we came up with additional functional requirements that we had to take care of. We now know that CPU and memory utilization was non-deterministic. The different data science processes that were running had different parameters, different data sets. We needed to account for those things as we were moving this into production. They were long running and often resource hungry, and we didn't know how hungry they would end up being. So there was also additional considerations we had to have for that. Also, being a small SRE team of 3, servicing about 30 engineers and 20 to 25 data scientists, we also wanted to see how closely we could get to our existing SDLC, because if we had to write a separate one for this, that would be a lot of cognitive load on us, and more importantly, a lot of toil. And that's what we're trying to avoid as an SRE organization. But also, how is this going to work in a live environment? What happens when our processes start to crash, or we needed to account for those types of situations? So as you might have been able to guess, we actually ended up going with daemon sets. Part of this is that we actually retain a lot of the orchestration capabilities that we have with the rest of our software. So applications, microservices and so forth, went through the similar process of updating, doing rolling updates, pushing new containers, reverting, rolling back. So that worked out nicely for us. But also, we gave each data science process its own resources with some light scheduling overhead and maybe some other daemon sets like FluentD that were running on the system to get logs. So, and also what's nice about this is that our scaling currency is infrastructure based. So for us to add more or turn down how many data science workloads we're running at any given time, we were essentially just adding new nodes to instance groups in Kubernetes, and the rest of the process was taken care of pretty seamlessly. And this is kind of just a short example. I spun up an ephemeral cluster just to kind of explain this. So here's a sample, one master, lots of worker nodes, and we would use a node selector just to isolate resources. And the daemon set, you can use a node selector to say, I only want these nodes to have this run. And then our backend API nodes would just have the same node selector, but for the API. So as you can see here with the pods underneath, these data science processes just essentially had what we were running on those 5 nodes that are the ones that are labeled here. So this ended up working out great. And kind of that led us to where we are today. We have the data science processes running as daemon sets. We have Python and Go microservices that are backed by a Ambassador API gateway, which is using Envoy underneath. We have Prometheus, Grafana, Elk, and Vue.js Nginx front end. Also using some middleware as well as Helm and FluentD as part of our logging. We also have some managed databases such as Redshift, RDS, S3, and we've been pretty successful with Airflow as far as data processing and pipelines. But this is great. This solves, I would say, half the problem. The other half of the problem is how do we scale? And there's 3 major considerations here. We don't want the person doing the scaling a human, because we're gonna burn out, for lack of a better term. Also, I can't just spin up 200 nodes to run data science because my boss is gonna call and say, why is the bill so high? I'm sure public cloud vendors don't mind that, but I'm sure our company does. But also too is we need to provide a great experience. Again, as I mentioned in the beginning, the requirements that have been set forth, but we don't want our client calling data scientists saying, this is too slow, can you just run this for me? That defeats the purpose of building the platform. So we do have data. We are running Prometheus, and as we were looking at some of our data science nodes, we see places where we can actually scale down. But the challenge here is that the time slice where you go from needing a node to having one is very impactful, because you're still waiting to be able to take on that next data science workload. So we actually needed to be about 10, 15 minutes ahead of knowing when we needed to have another node spun up to handle another data science workload. So as you can see here, this is a day time slice of the CPU utilization, and we kind of came to the conclusion that we could probably scale down some of our resources here and save some money, especially when you think of hourly prices and also some of the licensing that we have for different algorithms that run. So our solution essentially was to use time series forecasting. We had this great time series database, Prometheus, and we're actually using it to anticipate changes to key metrics, so our SRE team can right-size infrastructure, provide more redundancy during peak times. So if a client's on the West Coast, we know that we just scale up resources there instead of US East. And also reduce costs during non-busy periods. So employing that we have a collection of data scientists, I took this problem to them and said, what's the best way that we can utilize all of this data? And they were really excited about it. So we ended up going back and forth, and to be fair, there's a lot of different ways you can look at this data and model it. There's a ton of really great machine learning resources out there, but we ended up going with LSTM. And just a quick show of hands, how many people are familiar with neural networks? Okay, wow, okay. And how about long short-term memory? And one more, Keras. How many people are working with Keras today? Okay, all right, awesome. So what I'm gonna do for those so we can all level set, is I'm just gonna walk through long short-term memory, and I'm gonna breeze through a lot of the data science here, so please, if you have any questions or wanna go deeper, I'm happy to chat afterwards. In short, I mentioned it before, LSTM stands for long short-term memory. It's a type of neural network called an RNN, or recurrent neural network. And it's initially designed to recognize patterns and sequences of data. So a good example of this, you might have seen some papers. I think Google is working on something with image recognition and like working on different sequences of numbers and matching patterns. That's one of the common use cases for it. But when you think of a situation where I've been talking for about 10 minutes or so now, so you kind of know who I am. And let's say I said this paragraph, what would be like the next word you'd want to predict, right? So it could be Kubernetes, it could be containers, it could be Prometheus. Yeah. But it's probably not going to be something like bananas or sleeping. So, what a neural network is going to do is predict that next sequence. What's the next word potentially going to be? A couple of other neat ways that the community for machine learning and LSTM have been doing it is when you think of Mozart, for example, and let's say you listen to 10 hours of music of Mozart, and you have a new song, and you're 10 seconds in, a model would be able to predict the next musical note, perhaps, or be pretty close to what that would sound like. Let's say you took every work of Shakespeare, and you loaded that in. Essentially, works of art, or they're sequences, the sequence of words there. So what would be, if you got a paragraph of Shakespeare of some title you didn't know, could you predict the next word? That's another thing that an LSTM model would do. Also, time series forecasting. So this is something that's kind of more common in business. So if you think of, sales, revenue, you're always going to want to forecast out. I see investment bankers nodding their heads. That's good. So you're always going to want to forecast out, what's the next quarter or the next, 2 quarters to be able to kind of gauge your business. So LSTM models also play an important role there. So we decided that we were going to go down this path, and we were working with data scientists, and we had all this awesome data in Prometheus that we were going to use to actually shape how our Kubernetes cluster operates and the underlying infrastructure. So we would collect the metrics, and then those metrics would be fed in to build and deploy an LSTM model. That model would then be able to take in metrics that are streaming real time from Prometheus and make predictions. And we'll talk about that a little bit later. And then what we're working on now actually is taking those predictions and making decisions on the underpinning infrastructure. So there's certain things that we can do with Kubernetes. So you think of, if I predict 15 minutes out that I need to scale up my pods, I'm going to want to be able to connect to the Kubernetes API and scale that up. Likewise, if I need more infrastructure, then I'm going to talk to my cloud vendor and say, I need more infrastructure through another API. The reason why we're not there yet is because as we're still training these models, I don't want to bring down production. So this is not something that's deployed in production yet. But what we're working on is the observability of the predictions that are coming out, and my SRE team is actually adjusting that as we go. So we're still kind of fine-tuning, and we're still going through the discovery phase, but I'm going to walk it through each of these steps next. So the first one, which is pretty straightforward, is that we need to acquire these metrics. With this, you want to play with the data range, because ultimately, you're going to do a range query from Prometheus. The key thing here is that you don't want to take such a large data range, because if you think of your application, let's say you're a startup, and what your app looked like 6 months ago as far as traffic may not be what it is today. So how that model is trained is going to be on that full data. So you want to be kind of cognizant of, how heavily do I want to look at my traffic from 6 months ago and have that play a role in how predictions are generated. So what we do is actually 3 weeks, and as more folks are coming on and using the platform, we have a nice sliding scale of how the predictions are being generated. From there, we format the data, Prometheus, we're calling the API, getting JSON back, so we're formatting it into a way that can be loaded into a data frame in Python. And some example metrics that we've played around with just to kind of get an understanding of how modeling and so forth would work. Replica counts are kind of straightforward, get pod counts. Maybe you have an HPA that's already doing some stuff and you want to just predict where you are. That's one great way to do it. RPS, or requests per second, that's a key one that we've seen a lot where, every Grafana dashboard, I feel like, has one that is on display in the showroom. Also, upstream latency. So Ambassador has been great, and we've been using the underlying Envoy stats as a way to look at, which APIs of our Kubernetes service are being hit the hardest, and we can actually use that to figure out where do we need to scale, and we can train a model off of that as well. Lastly, you can just do plain old infrastructure. If you have node exporter set up and you're pulling in different metrics into Prometheus, you can pull those off a time series as well. So that's the first step. So you have your data. But one quick thing is that there is a limitation in Prometheus, but I wouldn't call it a limitation because you don't want to bring down your Prometheus server. So when you're making these large queries, you're probably going to want to batch them. And the reason for that is because there's a maximum resolution of 11,000 points per time series. So if you try to query your Prometheus server and say, give me everything from 6 months ago to today, and I wanted a rate of 5 minutes, not going to work. They're going to come back and say, reduce your time series. So a couple of things here. This is just kind of some commented out Go code. So we are basically taking the time and putting it into Unix time. So if you aren't familiar with Unix time, it's a 64-bit integer counting the number of seconds since January 1st, 1970. That's basically what Prometheus does when you set up the range of your range query. So from the from to the to. So that way you can batch that out really nicely and then basically aggregate it together and put it into the file for the data frame. Got a brief demo of it right here. So this is just one day, and it's going to basically grab 60 minutes at a time. You see the Unix timestamps here pulling all that together. And then we basically formatted it into a CSV, so it's just easy to load into another file system or the next part of the application. So it's going to take a look at the CSV. This is our dev server, so there's not a ton of activity. But as we scroll through, none of our developers are working late. Tisk, tisk. But then as we see, we go through here, and there's some RPS that's coming through. So this is kind of what the file looks like as you hand it off to the next step. So the next part is the interesting part. We're going to train and deploy the LSTM model. And this is largely, we chose Keras just because it's a very high-level API, and it's when you're just getting started with machine learning, this has been super helpful to go from nothing to something very quickly. And so the big thing that you want to do when you're starting out is take your entire data set, split it into what's test and training sets. I recommend with a time series doing, we do 60%. It's the first 60% of the data set is training, and the remainder is test. Then there's some transformation steps you need to do, basically transform the data into what's called supervised data. I could talk about that a little bit later. And then also scaling. So scaling basically takes it, the most common one to do is the hyperbolic tangent. It takes all of your data points and goes from -1 to 1. And then from there, you fit the model. And there's a couple of things here that our data scientists do to prevent overfitting. You may have heard of that, which basically means that you don't want your model to match your training set exactly, because predictions then are not going to be based off of anything other than the training set. So we do early stoppage and kind of more advanced topics, but I'm not going to cover that for this talk. But just know that there are ways of configuring your epochs and neurons on how you are fitting your model. And then after you do the training set, you want to evaluate the model against the test set. And that's the importance behind splitting them out, is that you can actually take data that was not trained and evaluate how predictions look. We're going to look at a quick model of that right now. So I have for you a IPython notebook. Good at showing up. And this is actually taking a very small data set, because we're actually going to run Keras really quick. So this is just showing some server latency that we grabbed from an Envoy metric from Prometheus. So you see here's your Unix timestamp. Here's some values that we have to play with. This is kind of the distribution of that data. So this is over about a day or so. And here we're actually going to run the Keras. So we see here, this is doing the training. The loss here is saying that, okay, it got a little bit better over time. Let me expand this out. So now our model is complete. that was relatively quick because the data set was small, and otherwise we'd be staring at this for a little bit. And here, we're going to take a look at our test set that we have, and we're going to run that. So we see pretty close. Seems like there was some, we were predicting 33 milliseconds, and it was actually 0. But these are pretty close to the actual latency for the test set. And importantly, this actually shows how well our model does against the distribution of the data set. So we're going to rerun this really quick. And so we might need to do a little bit more fitting. Typically what you're looking for is a linear, kind of like x equals y on the top right here. Let me expand this out. But this shows the predicted distribution on the left and the actual on the right, and these are the correlations between the two. So you're shooting for y equals x, but see here we have to probably do some different tuning and so forth. Okay, let's get back in. Oh, is this gonna, there we go. Okay, so now we have our model. So we're gonna now pass our model in to start generating some predictions. Now this is where it gets a little bit interesting because you're gonna choose a smaller data set that you're gonna feed in real time, but you still wanna have some context of what's happened, for example, in the last hour. Because if your model is saying like, it's dead, there's nothing going on, there's no request activity, but the real-time predictions are saying, no, there's someone using this right now, and we need to make sure that that stays up. That data gets fed into the LSTM model, and they account for that when doing forecasting. So we're going to basically use about an hour's worth of data to predict the next 10 minutes, for example. But you can kind of adjust this as you go. And then we're going to split the data set, again, into training and test data sets. And the training set, which could be, let's say, 40 minutes or so, is used to forecast the data in step. And then we're going to use the test set to basically do the next prediction. So if our test set is T0 through T4 here, we're going to use the data from that to predict T5. Now, you could be done with that and be good, or you could do something what's called multi-step. And you can basically do T1 and T5 to predict T6. Now, there's some considerations here. If your step is a minute, if each one of these is a minute, and that's a new prediction in actual, then what you're going to want to do is keep in mind you're going to have a higher rate of error the further you go out. So if I use this model and it's a minute, the predictions that are 15 minutes out are going to be more accurate than the ones that are 60 minutes out. So that's how in a nutshell, we generate the predictions. So now we have predictions to play with, and we have some actionable data. So what we have here, we have no traffic. So our predictions are saying from T0 to T15 that there's nothing. So what does this mean for me as an SRE? It means I may have the opportunity to scale down replicas and scale down some infrastructure. Conversely, if my RPS is going to go from 12 to 5,000, I'm probably going to want to account for that pretty quickly. So I have 15 minutes to basically get to a point where I can handle 5,000 RPS. And this is just kind of a very basic example. So if I had stateless resources, deployments, pods, there's some sample Go code here that basically says, I'm going to set thresholds that basically say, if we're above a certain RPS or below a certain RPS, then take action. Otherwise, let's sleep and wait for the next streaming predictions to take hold. Also, but I'm going to want to put gates in here, and this is why I actually mentioned it as like semi-supervised, and I don't know if that's the exact term, but there is human interaction here. We are preventing this from going way too high and way too low. Again, we're trying to not have a crazy cloud bill, but we also want to have our service up. So these are things to just keep in mind as you're going through it, and I can make these code snippets available on a GIST or something. And that's where we are today. From a data science side, we're currently exploring, can we do better? We're looking at kind of tuning those parameters, but also looking at something called multivariate LSTM. This correlation between some of your data, you may look at CPU percentage and RPS. and you may want to put both in a model and generate a different model off that may have more context to the rest of the cluster. Or maybe you have two different services that have different endpoints of latency, and maybe those models shape something else. So we're looking at multivariate LSTM as well. Another thing is reinforcement learning or Q learning. If you're not familiar, this is what AlphaZero or AlphaGo is based off of. We're looking at this as trying to reinforce good behavior. So if we, in a very simplistic term, if we say keep costs low, but make sure the client experience is optimal, and we define parameters around how that works, then we can use Q learning and use that to find a balance between maybe our threshold numbers as well as our min-max numbers that we were talking about in the predictions. And we're looking at other things that we can forecast. We initially started this out looking at how we can increase and decrease our infrastructure for our data science workloads. Now we're looking at it for replicas, and we're looking at it for different types of pods, even looking at it for some of the elastic resize stuff that came out for the databases. That's something that we're seeing if downtime's low, maybe we can do some scaling there. And also cluster management. Maybe there's situations where we can predict and move our clusters around, work in a hybrid environment and so forth. But I think the goal behind the data science part of this is how low touch can we get? What's the minimal amount of time an SRE needs to manage a Kubernetes cluster, and how much machine learning and potentially AI do we need to get there? And another thing that we're looking at is how do we make this intuitive and deployable? So we've been looking at HPA, horizontal pod autoscaler, and the model around that, and seeing if there's a way that we can take everything we discussed and actually put it into a CRD, or custom resource diagram. And then it's just as simple as doing a kubectl create PAS. I come from the PAS world, so that's kind of weird, but kubectl create PAS, that's something that attaches to your deployment or daemon set, and it's just intuitive. You pass some parameters and the machine learning starts to kick off. So this is something that we're actively working on, and that's it. So. I can take a couple questions.
I don't have a data science background. Does it take into consideration seasonality, like Saturday, Sunday?
Yeah.
Holiday?
So the question was, does it take into account seasonality? And that's something we looked at because, and I think the seasonality with like Saturday, Sunday, especially with what we were seeing with the Grafana charts, was kind of a primary driver for us. So when you're picking your slice of data that you initially are putting in to fit the model, that's important because then you're looking at, fall holidays, other types of things that are actually going to get incorporated in. So it's a balance between seasonality and, how stale that data is going far back.
So if a prediction went wrong, so let's say that the model predicted a certain number of workloads or a certain number of requests per second,
Mm-hmm.
do you guys have to manually adjust the number of nodes after that, or do you let it cover itself?
Sure, so that's a good question. So the question was, if the predictions were wrong, how do we adjust for something like that? So typically what we've been doing is that we also have a kind of a reactive. So if the model is bad, or maybe there's, it made an incorrect prediction and we need additional infrastructure, there's things you can do as far as like a reactive, kind of a correction. And you can keep track of those corrections as well to help fine tune your model. Or, ping Slack and one of us jumps on it and tries to figure it out. So that's another thing. Sure. So the question is around scale and how would this operate at scale. That's something we're looking into now. I think what we've initially done is unleashed it onto our development environment. So there's, it's smaller in scale, but as we start to look at it a little bit further out, I actually think that's where you see, if you decentralize and have like the model and have like a CRD for each different service, and your data sets you make your data sets a little bit smaller, you might be able to achieve the same level of kind of predictions for scale, but you have to just keep that in mind.
Have you automated the refresh of the prediction of the model?
Right. So what we are doing right now, the question was, are you automating the refresh of the model? Yes, we are. So basically, at midnight, we take in the next 3 weeks, the next rolling 3 weeks, generate the model off that. If the model fits the evaluation set, then we'll deploy it, and that'll be like the model that'll be used for the next day. And then from there, that process continues. So essentially, you can think of it as like a cron job that you would just kick off and then have the model created. We're actually running the model generation in Kubernetes as well.
When you do the learning, do you start with the previous model or do you start fresh?
Start fresh.
I'm wondering, beyond notifications, do you have another mechanism for exposing that semi-supervision that
Yes, I mean, so the question was, do you have another, you're asking about notifications as far as the semi-supervision, like if we're at like the max or the min?
Right, pretty much. Like if the model is giving you something that is different,
Right.
like how do you do that?
That's actually what we're doing now. So we're not actually taking the actions, we're kind of observing how the model is predicting. And if it's a ridiculous number, we're actually sending like a Slack message to our team to be like, hey, the prediction's way off. Can we look at it? How can we, is something wrong with the model? And we kind of do an investigation from there. Yeah. No. Yep, notification based at the moment, yep.
Are you doing anything like hold returns or anything on metrics? Like we have this workload?
Sure. So some of the things we're doing is like a rate over 5 minutes. So, and that actually plays into the resolution a bit. So you may have to do smaller batches when you do the rate resolution over 5 minutes. We've noticed that as we started smoothing a bit, the resolution for the time series got crazy. So I'll take one more. Sure. It's a good question. So why we use daemon sets instead of jobs. We initially went down, daemon sets gave us a bunch of benefits in the sense of we knew that we could run exactly one by using daemon sets on that particular node, whereas jobs, we didn't really get into heavy like affinity or node selection with jobs yet, but it's essentially triggered, and the daemon set is just listening for a job to appear in our messaging queue. So we're actually just waiting for it to pick it up, and then the data science process kicks off from there.